Welcome back. Today, we're jumping into a fascinating mathematical detective story. It's all about the search for certainty, about finding a situation where a problem can have one and only one possible answer. So let's start with a question that seems pretty simple. If you know exactly where a journey begins and you know the rules of the road, can you always predict where it will end? Seems like a solid yes, right? But, in the world of mathematics, this is a huge, profound problem. And the answer, well, it's way more complex than you think. You see, to predict any kind of path, you basically need two key things. First, you need the laws of motion, the rules of the game. Mathematicians have a fancy name for this, an ordinary differential equation, or an ODE for short. And second, you need that exact starting point, what they call the initial conditions. Put those two together, and you should be able to map out the whole trip. Should be. Okay, so here's our roadmap for today. We're going to start with this core idea, the uniqueness question. Then we'll dive into the weirdness of what happens when the answers start multiplying. After that, we'll uncover a really crucial clue about the start itself, we'll see the big breakthrough, and finally we'll unpack what it all means. For literally centuries, mathematicians have been obsessed with this search for certainty. They've been trying to nail down the perfect set of conditions that guarantee a unique solution. You've got some of the biggest names in the field, Peano, Osgood, Nagumo. All of them developed these powerful theorems to make sure that from one single start, there is only one possible future. And this is where our little detective story really kicks off. What happens when those laws of motion, that rulebook, which we'll call the function f, what happens when f is kind of mysterious and all those standard theorems just don't apply? The paper we're looking at gives us this beautifully simple, almost frustrating example. Look at this. We have two totally different paths. Solution 2 is easy. You just stay at 0 forever. Nothing happens. But look at solution 1, t cubed. It also starts at 0, but then it curves up and heads off. And here's the kicker. Both of these are perfectly valid solutions to the exact same equation, starting from the exact same point. So, poof, just like that, our ability to predict the future is gone. From one single, known past, you can get two completely different futures. That unique path we were looking for, it's gone. This is the heart of the problem we're trying to solve. Now, this quote from the paper shows you just how deep this rabbit hole goes. It mentions derivatives, which is just a way of capturing the motion of the system, its speed, its acceleration, how that acceleration is changing, and so on. The quote is hinting at an even weirder situation, a function that just seems to break all the rules of intuition. And here it is. I like to call this the phantom function. At its starting point at t equals 0, this thing is infinitely flat. Its position is 0, its speed is 0, its acceleration is 0, the change in acceleration is 0, you get the idea. It goes on forever. It's completely, totally indistinguishable from the boring 0 solution, and yet after a moment, it just springs to life. It's another, even more profound case of non-uniqueness. So facing this total breakdown of predictability, the authors of our paper did something really clever. Instead of trying to add more rules to the equation itself, they decided to look at the problem from a completely different angle. They looked at the start. They honed in on a very particular kind of starting condition. What if a solution starts out not just being still, but being extremely still? They call this a radically flat start. So what does that actually mean? Let's break it down. Okay, so first things first, the path starts at position 0. Simple, starts at the origin. Next, its starting speed is also 0, so it's not moving at the very beginning. Okay, still pretty standard stuff, right? But here, this is where the insight comes in. What if we keep going? What if its acceleration is also 0? And the change in acceleration, what physicists call jerk, what if that's 0 too? The big idea is to demand that a whole bunch of these initial motion properties are all locked at 0. That is what it means to be radically flat. And this quote from the paper just nails it. This is the absolute key. All that mystery about the laws of motion, about that function f, can be overcome. You're basically making a trade. The lack of information about the rules is compensated for by providing extra information about the extreme flatness of the start. So now let's get to the main theorem, the big breakthrough moment. This is where that whole idea of a radically flat start really pays off and solves our problem of having multiple possible futures. So the authors proved this incredible result. every one of these equations has something called an order, which you can just think of as its level of complexity. And they found that if you force the start to be radically flat, where the number of those zero derivatives is at least as big as the equation's order, then bam, the whole problem snaps into focus. There is one and only one possible solution. The ambiguity just evaporates.
Now, this is so much more than just a neat little mathematical trick. This breakthrough has these really powerful, almost unexpected consequences that tell us not just about the solution, but about the hidden rules of the system itself.
Let's just walk through this chain reaction of discoveries. So first, Theorem 1.2. This is what we just saw. If it starts flat enough, there is only one path. Great. But it gets deeper. Theorem 1.4 shows that for any given system, there's only one specific degree of flatness that makes it all work. It's like a combination lock that only opens with the right number of zeros. And here's the most amazing part, Theorem 1.5. It turns out that by demanding this specific flatness, you actually force those unknown laws of motion, that mysterious function f, to be well-behaved and predictable. In math terms, Holder continuous. You aren't just predicting the path, you're actually uncovering the rules of the road as you go. So here's the big takeaway from all of this. By being really careful and choosing an extreme starting point, we can do way more than just predict the future. We can actually reach into the guts of the system and figure out the fundamental rules that govern the whole thing. It's a way of forcing certainty onto a system that seemed completely uncertain. This just shows you the power of looking at a problem from a new perspective. And it leaves us with this really fascinating question. What other big, seemingly unsolvable problems in math or science or anywhere are just sitting there with a single clear answer, hiding in plain sight, just waiting for us to ask the right questions about their beginning? What mysteries could we unlock, not by finding new rules, but just by looking for a radically different start?